Key Ideas in Quantitative Finance, Ito's Lemma. Our problem starts long time ago with the work of mathematician Brooke Taylor. Brooke Taylor worked in calculus, and it had one of the many results that he contributed with to mathematics was what is called properly Taylor's theorem. We're going to make a link with this classical approach to mathematics, that is calculus, everything that we know very well, and something that happened in the past, in the 16th, 17th centuries, with something very modern, with another mathematician in the present or the recent past, and this mathematician is Kiyoshi Ito. Professor Ito worked not in calculus, he worked in stochastic calculus. And he worked in the equivalent of Taylor's theorem, but in the world of stochastic calculus. So in fact, there is a causal link here between both of them in terms of working the same problem, but whilst Brooke Taylor worked in the problem of calculus of deterministic functions and deterministic variables, Ito worked in the world of stochastic calculus, where we have stochastic or random variables and stochastic or random functions. They both arrive at the same result, but in the deterministic, calculus, or stochastic worlds. But what is this result? Well, we're going to start with calculus, what we know. And Brooke Taylor is going to keep us company. That's why he's on the top right corner of what we're doing. So, the problem of Taylor was to approximate a function. Brooke Taylor discovered that you can approximate a continuous function with another function, in fact a polynomial, that is denoted by f with a line on top of it, f bar, and this polynomial can be found by applying this formula here. This formula here is Taylor's theorem. Taylor's theorem says I can find the approximate function to describe another continuous function around a point. In this point we have x equals 0, it could be x equals a or another point, but around this point I'm going to find a polynomial of certain order that approximate this continuous function very well. So the more terms I use, the better the approximation will be. For example, I want to find f bar, that is the approximate function, for the exponential of x. I want to do this around x equals 0. What do I do? Well, I take Taylor's theorem that involves the value of the function at that point, f evaluated at a, involves the first derivative, and involves the second derivative, and so on. We're going to stop in the second derivative, second order terms, and if we evaluate the exponential in terms of the function of the exponential at 0, the first derivative, and the second derivative, what we're going to obtain then is a polynomial, and in this polynomial we are going to have a representation of the exponential function with very few terms. It is an approximation, it's a polynomial approximation, and we were able to do this using taking the derivatives of the original function. This approximated polynomial, we have it here in the dashed box, we have it in the bottom, and in fact if we look at the original function, the exponential, around point a equals 0, which is the point of interest, if we use one term or the first term of the approximation, well, we have the same values, but the slope is completely different. If we use two terms, then they start to look more alike. If we have the three terms, that is the full quadratic approximation, both lines become almost indistinguishable in the vicinity of a equals 0, the point of interest that we're trying to do. So this is Taylor's contribution, finding this approximate polynomial for that original function close to that point. We leave now the world of calculus, deterministic variables, and we move into stochastic calculus, where we have stochastic variables and functions. Here we're in the company of Professor Ito, and we start indeed with a function that is now a function of a stochastic variable x. Ito's lemma is the equivalent of Taylor's approximation, but when we have this stochastic variable and a stochastic function. And it is represented in this way that we have here. It is the same, or almost the same, as Taylor's theorem, is just expressed in a slightly different way, as we can see here. We see that if we apply it to 2 points, xi and xi plus 1, then by manipulating the formula, we obtain the representation of what is called Ito's lemma. But what do we use it for? Well, what we're going to use Ito's lemma for is to investigate what happens with the stochastic function when there are variations in the original argument, in the value of x. We can do that not only for functions of one variable, but we can do it for functions of 2 or more variables. Here on the bottom of the page, we have the function of 2 variables, and we have f that depends on s and t. We chose s because s represents the value of a stock and t represents time. And on the bottom right, we have Ito's lemma. Ito's lemma then tells us that a variation in the underlying is going to have an impact in the variation of the function, and they are related by these derivative terms that we see here. When we look at Ito's lemma and the problems, the type of problems that it can solve, they are slightly different from the one of Taylor. Even though the formula is fundamentally the same formula, what we are trying to find now is not the approximate function, is the change in the value of the function. The change in the value of the function, and this we called df, which is the increment in f. We have the arguments, the value of the stochastic variable described by the formula of that we see on the right, ds equals mu dt plus sigma dw, which is a stochastic differential equation known as an Ito process with constant parameters. And what we're going to do is first we're going to take Ito's lemma and we're going to substitute everywhere where we see ds, that is the increment in the value of the stock price, the SD, Ito's stochastic differential equation. The formula grows because we have all the terms, but by simple algebraic manipulation, we get to a new representation of this variation in df. And this variation in df, we see that can be related to the derivatives of the function in terms of the derivative with respect to time, the derivative with respect to the underlying, the second derivative with respect to the underlying, and these can be grouped in terms of the increment in time, the delta dt, and the increment in the Wiener process, that is the stochastic part of the problem. The solution of our problem then is this one. Through Ito's lemma, we were able to investigate what happens with variations of the function of an stochastic variable. And this is going to be very useful because this is going to allow us to investigate what will happen with the pricing of options or other types of financial derivatives, which are indeed functions of an stochastic variable.